We've talked about lists, and the biggest challenge with array lists as an implementation is the fact that they run out of space eventually. And so, I mean, we have our box shipping carts here, if you will, and each box will hold one thing. I know it might hold many of one thing, but it holds one thing, and you stack them all up, and they're really nice. And you can stack one of them on a truck, or you can stack two of them if you have one of those trucks that has a trailer behind the trailer. You can put a bunch of them on a ship, but every time you go to that bigger storage container, so you take a bunch of little things you're selling, you put them in a crate, and then you put them in the second crate, and you stack them and stack them and stack them. Every time you get bigger, you have to reorganize them all. So if you have like a whole bunch of them on a freighter, and that freighter breaks down, and you want to put them on a different freighter, even if it's a bigger freighter to move them along, you have to take each one off and put it onto the next one. It's kind of a pain. So in certain applications, it's unacceptable. It's too much work to constantly be getting bigger. You never know how big you're going to get. So that's why we have this notion of resizable storage. So let's say you go to the grocery store and you start filling up your cart, and at some point you fill up your cart, but you're not done yet. I mean, I haven't done this in years and years, but when I had a new family, especially when we first moved in the house, it was easy to fill up a grocery cart, and you need more at that point. So one strategy you can be is you can see carts, they're meant to stack. They're very stackable this way, but you can also bring in a grocery cart, and if this one gets filled up, you bring in another grocery cart and put a band between it. So just like carrying a trailer with a truck, or pickup truck or semi truck or whatever, and then you can take another grocery cart, put another band on it. You could have a whole chain of them. So you've seen them moving the carts empty through the parking lot, all stacked up and linked up, if you will. Um, they can do the same thing, with the carts otherwise. So each cart holds some stuff, and I can link one to the other. Now, we can use that same concept from the real world in our virtual world. So we can model the linking of our carts by saying the cart isn't the thing we care about. The thing in the cart is the thing we care about. That's what we're transporting. So again, instead of putting all the groceries in the cart, maybe we put one thing of eggs in one cart, and then the second cart has a big old heavy bag of dog food, and the third cart has a big old stack of, I buy water softener salt. It's very heavy and big. So the point is, a cart holds a thing. There's a stored thing inside of the cart, and then if I want to link our carts, my cart starts with one cart and then points to the next cart in line. And so it links to that next cart in line. So I push, or probably pull, one of the carts, given the analogy I had before, and then the other carts get towed along. And so this is a class diagram of showing that. This is a very software-y thing to look at. But we can look at an instance of that using a object diagram. So we start with cart one, and this is it. The thing I might store in cart one is spinach. I'm getting spinach, only spinach, but I don't want to get the spinach smashed. So I throw a second cart out there. The next cart in line stores my dog food. Big old 50-pound bag of dog food that I'm going to get. And then the third cart in line, well, that's where I'm going to put my Hot Pockets in it. They can't go by the spinach because the spinach is for the vegans and they don't like the smell of Hot Pockets or something. I don't know. Forget the analogy of one thing. In computers, it makes perfect sense. I'm going to keep track of a list of things, and I only need one thing inside of it, because whether it's one or 1,000, I just need to point to that thing, and we'll deal with a lot of pointers when we get into linked lists. So this chain of items is what's important and allows us to be able to extend out at any point. This concept is called a linked list. And so that cart concept is actually called a node. And in order to build this linked list, we start somewhere. And we start with something called the head. It's the starting point on the list. The head of the list is a typical name for it. And so the head of the list points to the first cart. So the first time we add something to the list, that first item, the first node we create, becomes the head of the list. And that node has a next cart it's going to point to, but that next cart isn't pointing anything to start with. It starts empty, or in software terms, is typically called null. So the null next pointer is a signifier of the end of the list. So the next time we want to add something to the list, we just start at the head. If the head's not empty, we keep navigating until we find the last node in the list by just saying, okay, well, cart1 dot next cart. Okay, well, that's cart 2. Cart 2 dot next cart. oh, that's null. So now we've reached the end of the list. So if we add a third item into the list, at that point it gets put on the second cart's end, and then the end of the list becomes the third cart's null pointer at the end of the list. And so that's how we add them in. We just start at the head. If that's not null, we just keep saying it. We iterate through them. While node not next is not equal to null, the next node is equal to node.next. And then node.next until we get down to when it's equal to null. And when it's equal to null, we add in we create a new node, throw the thing in that new node, a new cart, throw the thing in the cart, and then we attach that to the end. So since we have this data structure, then this idea of iterating through the linked list becomes a pattern across everything. So when I want to go get something out of the list, so if I want to go get something out of the array, let's say the fourth item of the array, I just say array sub 4, and it does some math and it jumps right to that item. Well, with a cart, it's a little bit slower. So if I want to get the nth item in the list, so the nth item being the second item, the ninth item, the 45th item, whatever numbered item outside of there, then I start with we'll start with the head. And if the nth number, the n is equal to 0, I just return the head. Otherwise, I keep counting until I reach the next one on the list. So I start with the head is 0. Head.next is 1. The dot next of that one becomes 2, and so forth. So I'm actually going to the n minus 1 in some cases, and in other cases I'm going all the way to the n. We're going to see the n minus 1 in a second. But when I'm retrieving an item, I basically count until I get to that item. So if I want the third item on the list, I just say, okay, well, it's not the head, that's 0, so the list is equal to null, and so while my count is less than 0 and it's not equal to, next is not equal to null, I just keep looping down this list. And we're going to see some of this when we get into code as we go further, but here's the concept of what's going on. I just keep walking down this, just saying, okay, the list I care about is equal to the next cart. The list I care about is equal to the next cart. The node I care about is next to the next one, until I've reached that count down there. I just can count through that. So once I find that list, I return that value. So the key to this is linked lists are really quick to add in, but as we just saw, they're much slower to navigate and to alter. I'm sorry, much slower to navigate, but they're quick to alter. So if I want to insert an item to a array list, so if I have a piece of paper with a bunch of names written on it, and I want to insert an item in that list, I have to basically rewrite the whole list, or at least everything that came after this point where I want to insert it. When I want to modify a list here, it becomes easy. If I want to insert an item at the nth item, so let's say I want to insert to item number 2, let's say. So when I'm doing insert, I find the node before the location. So I find the first node. And once I find the first node, I say, okay, well, that node, the node that is the n minus 1 node, its next is going to be equal to a new node. I'm going to create a new node out there. And so let's say I'm going to buy Coke Zero, and I want that to be the item number 0, 1, 2 on my list. Okay, remember, it starts at 0. 0, 1, 2 is going to be my Coke Zero then. And so I then set the next, that node, the one I'm inserting is next, to be to n minus 1, so the cart number 2 inside, it's next. And then I set the next of cart of n minus 1 to be the new one I created. So what I'm doing shouldn't surprise you. If you did it with cards on a table in front of you, it's very intuitive, but you have to be very methodical in working with lists to update these pointers and make sure everything points to where it's supposed to. If I mess up my pointers, I'm going to break my list in somewhere. I'm going to either throw away items or have it point circularly or something bad like that. So I have to be really careful. I create the new node. I point the new node's next to the rest of the lists by putting it to the next item in the list that was there, and then I just break that chain and fill it back in. All right, so this is the concepts that we'll get to practice in code as we move forward, but it's important to see that with these pictures and maybe practice it by working out on your hand with cards or whatnot. Let's talk about removing an item from the list. Let's say, you know what, actually right now, in 2020, Coke Zero is hard to find. So I want to get Coke Zero, but maybe they don't have it. Maybe it's not in my source. I put it on my list, but I need to take it off my list because it's not available or something like that. So again, to remove the nth item in the list, in this case 0, 1, 2, I'm going to remove the number 2 item, which is cart number 4, by the way. Notice they could be added in any order. The cart number here doesn't mean the order on the list necessarily because I'm inserting node in this case. But again, I got to find the node n minus 1. If it's the first one, the node n minus 1 is the head. If it's the 0th one, I'm inserting it at the front of I'm removing the front of the list, then the head is what gets changed right there. But once I find n minus 1, I can set, in this case, cart number 2's next cart is going to be equal to cart number 4's next cart. So I change next cart to be pointing to there, and then I basically, if I'm dealing with Java or Python or a garbage collection language, I leave it. I'm done. Cart number 4 will be picked up and taken out by the language. If I'm dealing with like C, C++, where I have to manage that myself, I probably should deallocate the memory for that, make it go away. But it doesn't matter that 2 carts think that the number 3 is the next cart. This cart number 4 is completely abandoned out there. It's going to just get deleted either by you or by the language eventually. Now, if again removing the 0th item, the high head, all I do is I set the head, the pointer to the head for the list, to be the initial head dot next one, and then this one goes away and it gets abandoned. But you see, modifying it is actually quite easy, as opposed to an array list, which I have to go to that item and then move everything up 1. I white out that item in the list and I rewrite the whole list, moving everything up 1, 1, 1, 1, 1, 1. So it becomes really difficult. All right, so the important thing about the remove, though, is you normally want to return the item that got removed. I'm not returning the cart, I'm returning the item. So when I say remove the second item of the list, I'm going to get back whatever that item was typically, which will be, in this case, Coke Zero. That's a typical implementation, just important to remember as far as the last bit goes. And so, again, most of the time, garbage collection will clean up after you. But if you're dealing in C or one of those languages where you have to manage memory, it's important to remember that. All right, so again, this is a high-level picture of data structures. This is a really favorite high-level picture of mine. This is actually from the Willis Tower, old Sears Tower. I've actually worked in this building, 37th floor, for a period of time. I worked in this building briefly, the Rookery building right here. I used to walk up and down here all the time. There's this. I just looked for a high-level view, and it came up with Chicago, and I was tickled. But the idea of this is it's a high-level view. It's important to understand these concepts. It's important to understand how these pointers go. Possibly someday somebody in an interview will ask you to draw a picture like I drew. How do linked lists work? We're going to dive into code. We're going to be working through the code as well as we go forward. So keep that in mind. Keep in mind that you're going to use these concepts when we go to code, but understanding it at both levels is going to be really important to really being able to successfully not just write the code, but understand it when it's working, debugging and testing it as well.